Pumps are expensive. So if one small pump won't be large enough, strong enough for your system, sometimes it's going to be cheaper to get two small pumps and combine them instead of spending all the extra money to get one really large pump. Then the question is, should you place your two pumps in series or parallel, which will give you more flow rate or more pump head for your system? And unfortunately, the answer is that it depends. Sometimes parallel will be better, sometimes series will be better. So I'm going to work through an example of exactly how you can compare your pump's characteristics against your system curve to help you make the decision as to whether parallel or series pumps would be better for your particular system. This is all going to start off with making a plot of your pump characteristics, put flow rate on the bottom horizontal axis and pump head on the vertical axis. I'm using gallons per minute and feet, but if your system's in different units, that'll be fine too. All right, your TA Serenity does not like making plots, so she went off and found a different resting spot, but we're gonna get back to work here. So in this case, rather than my pump curve being given to me as an actual curve, I'm just given flow rates, basically just X and Y coordinates that I need to plot. So I'm gonna put a bunch of black dots here on my drawing, connect those, and this is my pump curve for my pump. When you place two pumps in series, one after the other, they're gonna have the exact same flow rate through them, right? That's the continuity principle, like conservation of mass. All of the water that goes through the first pump all goes through the second pump, right? The exact same amount of water, but the extra pump adds additional pump head. So if the first pump adds 179 feet of head, then the second pump also adds 179 feet of head. So when you place two pumps in series, your pump curve gets twice as tall, but its width doesn't change. So the Q is going to be the exact same numbers, but I'll put out some green numbers here for series, and I've just doubled the pump head from the one pump to two because there's now two pumps in series. Plot these in green dots on my curve, and this is the series system, two pumps in series. And now when you place two pumps in parallel, their entrances and exits are connected, but flow takes a separate path to get from the entrance to the exit, right? Half the flow will go through the left pump, half through the right pump. So in this case, since the entrance and exits are the same, the pump head added by each pump will be identical to each other, but this time flow rate will be doubled, right? If the first pump can pump 500 gallons per minute, and the second pump's also 500 gallons per minute, then combined, they're adding 1,000 gallons per minute at the exact same 176 pump head. So I'm adding a new row to my chart here, parallel, where I'm just doubling all of the Q, all of the flow rate terms in gallons per minute, but keeping the exact same head. So when I plot these points on my plot, it just gets skewed out horizontally, but it's the exact same height. And now looking at this combined plot where you see both of them together, you can get kind of a clue as to how you're going to decide which one is going to be better. If your system curve is very tall and steep, sort of like example system 1, then you'll notice that the point where the system curve and pump curve crosses the series set of pumps is up and to the right of the parallel. This means series would be better. You'll get more flow rate at a higher pump head using two pumps in series. And in fact, for a very steep system curve, the parallel actually performs almost the same as having just one pump. It really would be a waste of money to go from one pump to two pumps in parallel. Those intersections with the system curve are almost right next to each other. Oppositely, if we look at the red example system 2 line, you'll see that for a flat, a relatively shallow curve, system curve, parallel is going to be better. Right? In this case, the light blue intersects the red line further to the right and higher, so parallel pumps will give you both more flow, like a larger Q, larger flow rate, and higher pump head than either series or one pump. And in fact, the series and one pump actually behave kind of similarly at high flow rates, low pump head. Okay, so now we sort of understand series and parallel pumps and what we're looking for when we compare the system curve. So We need to actually draw the system curve, and that's where basically all of the work actually comes in, is in understanding your system. So based on my system characteristics, 1,200 feet, 12-inch diameter, some minor losses, a change in height, I'm gonna go ahead and draw a picture, right? It's always gonna be easier with a picture. Every engineering problem you ever solve, draw a picture. That's always just gonna be part of it. So I'm gonna assume I'm going from one tank to another tank, pumping through a couple of elbows. I've added a gate valve here and a change in height so that tank B is 50 feet above tank A. I've got an open gate valve and a 90-degree elbow. And I forgot at the moment, I'll draw this in later, there also has to be a pump here in the problem. So again, there's no drawing on the pump right now, but I'll come back in a couple of minutes. You'll see it kind of randomly appear on here. And of course, once you make a drawing, then you write down some equations. That's the whole point of making a drawing, is to make your equations from the drawing. So a system curve starts off with the energy equation, right? This falls under the category, if you're looking up in a textbook, of probably conduit flow or flow through pipes. And so that's the energy equation. So I need to find 2 points along a Bernoulli flow line. So I'm going to choose point A and point B from the top of each tank. And if you have a tank, the top of the tanks is always a great place to choose for points, because a ton of terms in your equation are going to cancel out. So my energy equation, right, pressure over gamma, because I'm going to be working in units of feet. So V squared over 2G plus Z plus pump head, right? That's the energy added by the pump in the system, which of course, when I started writing down this equation is why I recognized that I hadn't actually drawn a pump in my drawing. And yeah, so it's there now. Right side of the equation, pressure B over gamma, V squared over 2G for point B, ZB, and head loss. The pressure terms on both sides are going to cancel because they're both exposed to atmospheric pressure, so it's exactly the same. The velocity terms are also going to disappear. Even though there is velocity through the 12-inch pipe, I'm going to assume that the tanks A and B are very large, and the actual change in height in the tank is going to be very slow. So VA and VB are not the velocity through the pipe, they're the velocity of the change in height of the top of the tank, which I'm going to assume is 0, close enough. That leaves us with just the change in height plus head loss is pump head. So the amount of energy added by the pump has to overcome head loss and pump up 50 feet. And it seems like we're almost done. All we have to do is find head loss. Of course, head loss is like everything, so we're still nowhere close to being done. So head loss is going to be divided into major losses for friction and minor losses for all of the extra components in the system. So the friction, I'll use the Darcy Weisbach Equation, which is also this F is gonna come from the Moody Diagram. So FL over D, V squared over 2G. The length 1,200 feet and diameter, I'm gonna do 1 foot to make sure the units cancel out, not 12 inches. And the biggest, easiest thing for a student to mess up is that G is 32.2 when we're using feet units, right? Not 9.81, which is metric system. So for minor losses, a summation of K V squared over 2G for all of the different features. So as I sort of trace a path through the system, I come across 5 different features that will have minor losses. The entrance, the 90-degree bend, the other 90-degree bend, the open gate valve, and then the exit into the tank. So all sorts of places that you can look up values for minor losses. I'm going to pull up the FE reference manual, which has a nifty little figure here for the entrance and exit. Get a K value of 0.5 for a square entrance. I'm assuming it's not rounded. Sure, make a good assumption there. And for the square exit, also K5 is 1.0. I'll do something a little bit different here for the 90 degrees in the open gate valve, though. If I look up in Fox and McDonald's textbook, table 8.4, they have these minor losses not written as K. They write them as LE over D. And the numbers are gigantic, right? 30, 30, and 8, right? Compared the entrance is 0.5, and this L over D is 30, right? It seems really high. This L over D, this 30, what this actually represents is an equivalent length. So this table doesn't treat minor losses like a K term. Instead, we're treating these like length over in the friction side of the equation. We're essentially saying that this 90-degree bend makes it seem as if the overall pipe, instead of being 1,200 feet long, is an extra 30 feet longer. It's 1,230 feet long. So it gets multiplied by friction. So what I'm going to do is I'm going to take these 90 degree and this and the gate valve value, this 30, 30, and 8, and sort of move those over to the friction equation as extra length. 30, 30, and 8, an extra 68. I'm going to treat this pipe like it's 1,268 feet long. So that's another way to treat minor losses. One way is to treat them as K. Another is to treat them as extra length. You can use both. You can mix and match. It doesn't really matter. It'll work out either way. So my head loss equation, I've got friction multiplied by 1,268 plus 1.5 for my minor losses times v squared over 2g, which I'll write as 64.4. And if it weren't for this f, we would be basically done. This would be really close. F is going to be kind of tedious because unfortunately, while there are some equations that sometimes work for f, really the best way for f is the Moody diagram. And when plotting a plot, that means we probably are going to have to actually look up every single point that we plot to find a different f value at every point, because they're all going to be different. At every flow rate, there's going to be a different velocity, different Reynolds number, different friction factor. So we got to organize ourselves. So we're going to just go ahead and make a table, right? Ultimately, what we're trying to do here is to plot pump head on the vertical axis versus Q on the horizontal axis. So Q is our input, and Q is not even in this friction equation for head loss. So we're going to have to convert Q to velocity. Velocity is in the equation. So Q is A times V, cross-sectional area, times velocity. Our area, pi over 4 times 1 squared. We're just 1 is the 1 foot, so not 12 inches. We're using feet. So we get 0.7854 feet squared. But we're also going to have to convert the units. We want velocity in feet per second, but Q is in gallons per minute. So we're going to use the best conversion factor ever that I never forget. And any gamer out there should always remember how to convert gallons to feet cubed, because it's LEET. 0.1337 feet cubed is 1 gallon. Once you see it, you'll never forget it, right? It's the easiest one. 1 minute to 60 seconds. So we get a conversion here, 2.228 feet squared per second, feet cubed per second for Q. So to get V from Q, we take Q divided by 1,000 times 2.228 divided by 0.754. That converts Q in cubic feet per, no, Q from gallons per minute to our V in feet per second, both from the equation over V and the unit conversion all in one. So I actually solved this in Excel. I just made like a spreadsheet and just typed in this equation once and just kind of like did a copy down the row to fill this in. But I still just wrote them all down here by hand for some reason instead of putting the screenshot of the spreadsheet up on the screen. You could put all these in your calculator if you wanted to, or use Excel so you only have to put in one and then you just copy the equation down. That can save some time. All right, so all the velocities. In order to get the friction factor, we're going to need Reynolds number. So Reynolds number, V times D divided by viscosity. And I always forget which viscosity is which, so check the units. My numerator is feet per second for velocity and feet for diameter. So I want the viscosity that has units, feet squared per second. So that is the one that looks like a cursive V, right? The Greek letter nu. And so I'll go to my table here, assume standard temperature and pressure 59 degrees, and make an assumption that my value for viscosity is 1.23 times 10 to the negative 5th feet squared per second. Again, I can just put this equation into my spreadsheet and just have, the cell right next to it times this divided by that, and then just copy it down. Basically starts off with 2.3 times 10 to the 5th, and then all the way at the bottom, 1.6 times 10 to the 6th. One more thing before I can go to the Moody diagram is the roughness. We need to know of all of the different curvy rows in the Moody diagram, which rows are we in between? And I'll just assume that this is commercial steel pipe, which I'll go ahead and look up and get an E value of 0.00015, that's 3 zeros. Diameter of 1 foot, so my roughness row, 0.0003015. And unfortunately then for the F column in my chart, there is no way to just do this in Excel. So I'm just gonna individually have to go to the Moody diagram and look up. So for this same roughness value, for all of these different Reynolds numbers, look up the value for F. So I get these starting from 0.0167 down to 0.0136 down at the bottom of my chart. But now that I have V and I have F, now I can go back to Excel. So that now I'm using my head loss equation and I'm referencing both the F row, the F cell and the V cell, plugging those in and find head loss. So at 1,000 gallons per minute, head loss is 3 feet. And all the way down at 7,000 gallons per minute, I have 115 feet. And last column, finally, the pump head equation. Come back over to this equation from all the way back at the beginning of the problem, a million years ago, right? Pump head was just head loss plus 50. 50 was the change in elevation. So that's how much energy is supplied by the pump is to overcome friction and minor losses and raise it up 50 feet. So we just take head loss plus 50. That gives pump head. This is the system curve. Finally, after all of these columns, a million calculations, use the Moody diagram a billion times. This is your system curve. And now we can go back to the original drawing where we have the pump curves and plot our new actual system and finally see whether this particular system would do better with parallel or series pumps. And so I'm plotting each of these points as black dots on my system. And you can see that this system curve is even lower, like even flatter than my example system 2. And so highlighting each of these operating points, so where the pump curve crosses the system curve, that is going to be your actual operating conditions. That's the actual flow you will really get through the system and the actual pump head that is supplied by the pump. So because this is a very shallow flat curve, you can see that the one pump and the series conditions are almost next to each other. So going from 2,800 gallons per minute with one pump, we'd only increase to about 3,000 gallons per minute by adding a second pump in series. So this would really be a waste of money to add an extra pump in series. You get hardly any extra performance, maybe 10% extra performance for double the cost. But for parallel systems, we get about 4,600 gallons per minute, about 100 foot of pump head added. So we're going from 2,800 gallons per minute to 4,600 gallons per minute. That's not quite double the performance, but maybe 75. Actually, why don't I just use a calculator? So 4,600 divided by 2,800. Yeah, we get 64% improvement. Why was I gonna guess? Just type it in. So 64% improvement. So we get double the cost for 64% more flow. And now you're never gonna get literally double the flow. The only way that could happen is if your system curve was perfectly horizontal. If it's increasing a little bit, you'll never get double. But again, getting 64% more flow for double the cost, this might be more beneficial than using a single larger pump. It's possible that just having one gigantic pump might cost 5 times as much money. So actually, maybe double the cost is actually better than the alternative. So one thing this video does not cover is pump efficiency. Even though a system curve and a pump curve do overlap and the pump will work, doesn't necessarily mean that it's operating at an efficient power level for that pump. So watch this video on the screen here that talks a little bit about pump curves and efficiency.